Alright, so what we've got in this question is a cliff right here, okay? And then you've got a ball that's rolling along the cliff and then rolls off, okay? So now, this thing isn't shot at an angle, it's not shot upwards, it's not shot downwards, it just rolls off. So all of its, if you think about this moment right here before it rolls off, all of its velocity is strictly going horizontally. There's no vertical velocity at all. So I know, as a result, this thing is being shot at 100 meters per second. So all of that velocity, v1, is going to be horizontal. So v1 is going to be equal to the horizontal velocity, which is then going to be 100 meters per second. As such, we mentioned that this thing has no vertical velocity, so it's 0 meters per second in this case. Okay? Alright, so then we're going back to our quadratic equation, which is given to you, of course. So it's dy equals v1 yt plus 1/2 at squared. What I'm going to do is put my coordinate grid in a certain spot to make the problem a bit easier to solve for me, that's all. So what I will do is draw my coordinate grid right here, okay? So in this case, this is essentially at the origin, 0, 0, right? So I've got my x coordinate and my y coordinate, okay? This thing goes down here and then essentially hits the ground. So when it's at this point, the change in displacement from the initial, well, you can think of it as really being 500 meters, because this is 500 meters here, 500 meters below its starting point. So in this case, we're taking upwards to be positive, downwards to be negative. So this change in displacement here is negative 500 meters. As we mentioned, v1y is 0, so this term here just goes to 0. And then I've got plus 1/2 at squared, so that's 1/2 of negative 9.8 t squared. I don't know what t is. T is essentially how long it takes this thing to hit the ground. Or, if you want to think of it in terms of the quadratic function that's drawn, it's really the x-intercepts of the quadratic function. Okay, so back here, simplifying this, so this is negative 500 equals negative 4.9 t squared. I just solved this for t now, so I would divide both sides by negative 4.9, divide by negative 4.9, so that gives me t squared equals 500 divided by 4.9. As such, t is the square root of that, which gives me approximately 10.1 seconds. So what that tells me is that this thing takes 10.1 seconds to hit the ground here, so it's my x-intercept. So now we should know that distance is just equal to speed times time. So in this case, my horizontal distance should be equal to my my horizontal speed times how long it's in the air. Okay, my horizontal speed, as we mentioned back here, is 100 meters per second. So it's 100 meters per second times 10.1 seconds, which I did not calculate actually, but that's your final answer right there. So that's part A. For part B, this one's a little bit different, but we're going to essentially take the same kind of process. So we've got this thing, and it's being shot upwards now. So just conceptually, you can imagine that instead of just rolling off and landing right here, it's probably now going to last a bit longer in the air. So if you think about what the velocity vector right here looks like when it's being shot, well, it's really a bit like this, right? Here's the point where it leaves the cliff. Its velocity is split up that way at 100 meters per second, okay? Now, anytime we're dealing with vectors, especially in a projectile motion here, we're going to have to look at the horizontal and the vertical components of the two vectors. So I've got the horizontal component right here, the vertical component right here. Of course, they form a nice right triangle. So I could call this v1x. This is my v1 here, of course. this would be V1y. My angle, of course, it was shot at an angle of 60 degrees above the horizontal. So here I have essentially a right triangle, and I'm just using a bit of trigonometry. So if I look at this is my angle. The side that's across from my angle is my opposite side. The side that's next to my angle is my adjacent side. Of course, this is my hypotenuse here. So if I look at, say, V1x, well, this is adjacent and hypotenuse. Of course, if we remember our basic trigonometry, adjacent and hypotenuse would be the cosine ratio. So I know that cosine of 60 degrees is equal to adjacent, which in this case I'm going to call V1x, over my hypotenuse, which is 100 meters per second. Solving this now, well, I could just cross multiply now. So V1x times 1 is V1x. 100 times cos 60 is 100 cos 60. And actually, the cosine of 60 degrees is just a half. So this is really 100 times a half, which gives me 50 meters per second. Okay? Now, vertically, I would be looking at now the opposite side. So opposite with hypotenuse would now be the sine ratio. So my sine of 60 degrees would be equal to, in this case, my opposite, which is V1y, over my hypotenuse, which is 100. Setting over 1 and then cross multiplying again. V1y times 1 gives me V1y. 100 times sine 60 gives me 100 sine 60. So that gives me 86.6, actually 7 if I'm rounding properly, meters per second. Okay? So that gives us the components of our initial speed. Okay? So moving on now, we're going to go back to the quadratic. So the same quadratic equation that we used before. So dy equals v1yt plus 1/2 at squared. Now notice d1y, this is still here, a height of 500 meters. So from start to finish, you can think of this again with, my coordinate grid in the same spot, right? So this point is going to be 500 meters below the starting point, or a negative 500 meter change in displacement in the vertical direction, sorry. So my dy here is going to be negative 500. My v1yt, well, remember v1y we just calculated to be 86.7. T, I don't know, of course, that's the x-intercept again. Plus 1/2 at squared, so plus 1/2 negative 9.8 t squared. Simplifying this now gives me negative 500 equals 86.7 t minus 4.9 t squared. So you see, I'm ending up with a quadratic here. So I want to set this up as a quadratic equation in standard form. So ax squared plus bx plus c equals 0. So to do that, all I'd really need to do is to get rid of this from this side and put a 0 right here. So to do that, I'd need to get rid of this and subtract 500. Well, to get rid of subtraction, I would add 500. So add 500 to this side. What I do to one side of the equation, I have to do on the other side. So I add 500 to this side. Okay? So that gives me 0 equals 86.7 t minus 4.9 t squared plus 500. And now, just to keep it a little bit clean, I'm going to write this in descending order so that I can clearly see what A, B, and C are when I enter into my quadratic formula. So here I can see that A is negative 4.9, B is 86.7, and C is a positive 500. So using the quadratic formula now, so negative b plus or minus the square root of b squared minus 4ac over 2a. I'm not going to go through this step, but you're going to get two solutions, two x-intercepts, which should make sense. If I go back, oops, that's the previous one. If I go back to this, I should have an x-intercept right here, and I should also have one actually over here if I were to continue it, right? Okay, so I'm usually going to get one positive x-intercept and one negative x-intercept, which when I do this calculation with my formula, I do get a negative 4.6 and a 22.3. So, of course, in this case, having a negative time value doesn't really make sense in the context of the problem. So I reject this t value. So that tells me that this thing takes 22.3 seconds to hit the ground. Again, now, to finish off the problem, my distance is equal to my speed times my time. My horizontal speed is still, actually now it's 50. Remember, we did this calculation back here. It's 50, right? So my horizontal speed is 50 meters per second. My time now is going to be 22.3 seconds. And multiplying this together will give you how far that thing travels in this instance. Okay, now part C actually is really similar to part B, and it's going to work really similarly. The only thing that's different is that it's shot downwards. So when I draw that, it it gets kind of pushed down like this. So it should make sense then that if it's pushed down, it probably shouldn't travel as far. So in this case, I've really got a 60-degree angle right here, right? So when I draw my velocity vector, it actually looks a bit like that, right? It's still 100 meters per second, but when I draw my components, they're actually up here now. My right triangle I form with a 60-degree angle. My horizontal component will be right here. My vertical component will be right here. So again, if I'm looking at v1x, this is going to be, well, this is opposite. This is adjacent. So it's going to be adjacent over hypotenuse. So I can say cosine of 60 degrees equals v1x over 100. Cross multiplying now. So v1x I can see is 100 cos 60, which gives me cosine of 60. So it's still going to give me the 86.7, right? No, cos 60 is half, so 50. Right. Thinking of sine there for a second. Now when I look at my vertical component here, I'm going to be looking for the opposite side. So opposite with hypotenuse will be sine again. So sine 60 equals opposite, so v1y over 100. Write this over 1 and cross multiply again. So v1y is 100 sine 60. Okay, I'm going to come back to this for a second. So that numerically would give me 86.7. But think about this in the context of my problem. I'm putting my coordinate grid right here again. All right, and the previous one, you notice, was shot upwards. So the velocity here was given a positive in the x, because these would be your positive x values, these would be my negative x values, these would be my positive y's, these would be my negative y's. This was why this was negative down here, negative 500. So in this case, since it's shot upwards, my initial velocity in the horizontal and vertical were both positive. Now you notice in this one's shot downwards. So if you look at my x values here, everything is still to the right of my origin. So when it comes to my x values, these are completely fine. They're still positive. But this is really shot downwards, right? Of course, these are my negative y values. So when I do this, this actually should be thought of as a negative 100 and a negative 86.7. Okay? That's really the difference from B to C. Oops. So then finishing out, let's see what I've got now. We're going to go back to that quadratic again. So dy equals v1y t plus 1/2 at squared. This is still a negative 500. Now v1y is negative, so this is negative 86.7 t. This still becomes the same thing, so minus 4.9 t squared. Again, setting up my quadratic equation in standard form. I need to move everything to one side, so I'd have to add 500 to this side, add 500 to that side. So that gives me 0 equals negative 4.9 t squared minus 86.7 t plus 500. Using my quadratic formula, you actually notice I get the same numerical absolute values as last time, but the signs are now flipped. So I think it comes out to be a negative 22.3 and a positive 4.6. So of course, doesn't matter what this is, that's a negative value, doesn't make sense in the context of this. So we're going to use the positive value. So of course now dx equals vxt. So this is going to be, my horizontal speed was at 50 meters per second times 4.6 seconds, which now gives you your range for part C. And that's it.